Welcome to my presentation about mitigating retention failure using approximate scrubbing in neuromorphic fabric based on resistive memories. I am Soed Tuhin Ahmed. I am from the Department of Computer Science of the Karlsruhe Institute of Technology in Germany. In literature, it has been shown that neural network can solve complex computational tasks with a high degree of accuracy. Neural network can be implemented in hardware efficiently with emerging resistive memories. But the hardware implementation of neural networks suffer from retention faults where the stored data is not retained due to external influences. These faults accumulate over time and can severely impact the performance of the implemented neural network in hardware. Normally, ECC-based scrubbing is employed to recover the corrupted data in memory arrays. ECC-based scrubbing adds redundant database to the memory and can detect and correct failure within a certain limit. Since neuromorphic computing needs large number of NVM arrays, a significant number of redundant cells will be required. This overhead is not practical for neuromorphic computing. Also, the encoding and decoding circuit required for the ECC-based scrubbing is difficult to realize in analog neuromorphic computing. Hence, in this paper, we propose a low-cost approximate scrubbing to mitigate retention failures. Here is my outline for this talk. At first, I will give introduction to this paper, then I will give some background so that the rest of the talk can be understood better. Then I will talk about our proposed approach and present briefly our results. Then I will conclude this presentation. Complex computational tasks like image recognition and sensor data processing for Internet of Things devices, for example embedded devices, are the focus of modern computer architectures. Neural networks offer a compelling solution to this problem due to their high performance in cognitive tasks. Neural networks are biologically inspired computational graphs constructed out of neurons that form their fundamental building block. There are several classes of neural networks available, but the most basic one is this densely connected neural network. A single layer of a network can be described as this metric vector multiplication of the weight matrix and the input vector, followed by addition of biases. Several of these layers can be connected together to form the neural networks. Inference of the neural network is usually carried out in computation-centric architecture such as graphical processing unit or central processing unit. Computation-centric architecture offers flexibility, but they are highly inefficient due to data movement between the processing unit and the memory. This results in the well-known von Neumann bottleneck, which becomes the bottleneck of the entire system. As a result, such type of architecture is not suitable for the implementation in resource-constrained systems. Emerging non-volatile resistive memories offer a promising avenue to accelerate deep learning application with neuromorphic compute in memory, where the training and the inference of the neural network can be performed efficiently and directly in memory. Hence, the expensive data movement is not required. Three such type of devices are resistive RAM, phase-change memory, and spin-transfer torque magnetic RAM, which has magnetic tile junction as the storage element. These two terminal devices store and represent data as a resistive state. They can be programmed to low resistive state or high resistive state by applying voltage or current through them. Such devices have many advantages such as zero leakage power, scalability, non-volatility, and so on. Usually, neural networks have fixed point weight and activation that require higher memory size to store the trained weight of the neural network, and they are computationally expensive. By the neural network binarizes all the weight and intermediate activation to +1 and -1 during inference, and they require only one bit to store the trained weight of the neural network. By reducing the bit width from multi-bit fixed point to single bit per weight, we can directly map one layer of a neural network to a crossbar array. One-time write operation is performed to map the train weight of a neural network to a crossbar array. Resistive values of the NBM cell. This represents the neural network weight. In this paper, we encode positive weights as a resistive state and negative weight as a low resistive state. But this can be decided based on the NBM technologies. Multiple word lines are activated at a time, and the weighted sum operation is performed in parallel. Retention failure are mostly unidirectional in NBM technologies. That is, a cell in one state is more likely to switch to other state than other way around, because of the energy barrier a state has to overcome to move to the other state. But the nature and the direction of the faults are technology dependent. For example, in STT-MRAM, the state change from high resistive state to low resistive state happens suddenly, but in VRAM the state change happens gradually over time. One of the design methods to mitigate retention failure in STT-MRAM is to increase the thermal stability via increasing the cell dimension, but this increases write energy and latency of the MTJs. In phase change memory, the unused resistance ranges between the resistive states can be increased to mitigate retention failures. Now, for the proposed approach. Our proposed approach is based on the fact that neural network can tolerate certain amount of retention failures without suffering too much inaccuracy, which has been shown in previous studies. Also from the fact that retention failures are mostly unidirectional. Based on these two facts, we divide our crossbar into two regions. One is the scrubbing region where all the unstable weights are stored, and another is the non-scrubbing region where all the stable weights are stored. And the scrubbing region is frequently scrubbed to prevent accumulation of faults. For this, a scrub controller receives a scrub region shape and scrubbing frequency, and it rewrites the scrub region row-wise or column-wise to restore its respective grade. Scrub frequency can be chosen based on NBM technologies and environments such as operating temperature. Our proposed scrubbing technique only corrects unidirectional retention fault in the scrub area only. Thereby, it only approximately restores the intended weight matrix in the NBM memory. Hence, it is termed approximate scrubbing. But there are two challenges associated with this technique. Since each scrub area requires storing information about the size of the scrub region, ideally the definition of the scrub area should be kept constant to avoid significant memory overhead. With that in mind, there are several types of scrub area can be defined. For example, the square-shaped scrub area, which requires 2 points to store per scrub area. But the square-shaped scrub area leads to low variation in the weight of a neuron. Hence, in this paper, we implement diagonal-shaped scrub area, which define a diagonal which divides the top right part of the crossbar into scrub area and bottom left part of the crossbar into non-scrub area. Increasing and decreasing the diagonal value can be visualized as moving the diagonal towards top right or bottom left. The value of diagonal is considered hyperparameter during training. In order to explain this better, the crossbar structure will be represented as a simplified weight matrix from now on. Scrub and non-scrub area of the crossbar have approximately 40 to 60% +1 and -1 weight respectively, without any training modification. Negative weight stored in the scrub region will be overwritten to +1 weight through scrubbing, and the positive weight stored in the non-scrubbing region are subject to retention failures. The combined effect of these two will lead to massive amount of degradation in the inference accuracy. Hence, in this paper, we propose a neural network training technique with a penalty function. The penalty function encourages the neural network to store most of the +1 weight in the scrubbing region while minimizing the negative weight. Conversely, since the non-scrubbing region is not scrubbed, it encourages the neural network to store most of the negative weight in the non-scrubbing region while minimizing +1 weights. The proposed penalty function is combined with the loss function to form the complete training objective. The rearrangement of weights post-training, that is, moving all the positive weight to the scrubbing region and all the negative weight to the non-scrubbing region, is not possible, because in a normal crossbar structure, interconnects are fixed. Hence, the relationship between the input and the output cannot be maintained. Now for the result section, our simulation setup is as follows. For each evaluation run, we have trained two models. One is the reference model and other is the proposed model. The training of the reference model is unaltered and is not scrubbed during the evaluation. The proposed model is trained with our proposed training algorithm and it is scrubbed during the evaluation. During the training and the evaluation, we have used MNIST, Fashion MNIST, and Cypher3, which is a subset of Cypher10 data. This paper is focused on the unidirectional retention fault in the MTJ-based crossbar, but the proposed method can be applied to mitigate retention fault in other emerging NBM-based crossbar. Faults are injected into the hidden layer of a neural network only, because the hidden layer have more parameters compared to the input and the output layer. Also because the input layer's input and the output layer's activation are not binarized. Input layer and the output layer weight are mapped to a crossbar with high thermal stability. We have evaluated different crossbar one at a time for each of the MNIST, Fashion MNIST, and Cypher3 datasets. Our simulation result shows that initially the inference accuracy of the proposed model is slightly lower. But the proposed model performs significantly better towards the end of the expected device lifetime. Our proposed scrubbing technique improved the inference accuracy by more than 82% in MNIST dataset, 74% in Fashion MNIST datasets, and 30% in Cypher3 datasets. The scrub and non-scrub area contain only their desired value, hence, for our proposed model, inference accuracy doesn't degrade from its initial value. Previously, we showed results when the thermal stability of the crossbar is constant. But when the thermal stability of the crossbar is varied, our result shows that the inference accuracy of the reference model varies, but the inference accuracy of the proposed model does not change, given that the crossbar is scrubbed with sufficiently high frequency. The inference accuracy of the proposed model is significantly better in the long run when the thermal stability of the device is low. Now I will conclude this presentation. In conclusion, neural network can solve complex computational tasks with a high degree of accuracy. Neural network can be implemented in hardware with emerging non-volatile memory very efficiently. But the hardware implementation of neural networks suffers from retention failure, which decreases the performance of the implemented neural network. To mitigate this retention failure, we propose a low-cost approximate scrubbing. It defines a diagonal which divides the crossbar into a scrubbing and non-scrubbing region. Our proposed approach has virtually zero memory overhead, but can improve the inference accuracy of the device up to 85%. It enables higher density of the crossbar and allows reduction in write latency and energy of certain NBMs without trading off the retention time. Thank you for listening.